Welcome. Today I'm going to start the topic that is CFSE. The topic is crystal field stabilization energy. So this is also we can say that CFSE. CFSE. Okay. Also you can say that CFSE. So what do you mean by a crystal field stabilization energy or CFSE? So if you define it, then this is the energy released by redistributions of p orbitals in the presence of ligand. Crystal field stabilization energy is called that one type of energy which is released by while we are doing redistributions of d orbitals, and that is in the presence of ligands. Okay, so that energy is called that CFSE. Okay, so this energy is called crystal stabilization energy or CFSE. Now, so how actually that energy is released? Let's say we have the d orbitals. The d orbitals 5 will be there, 1 2 3 4 5 orbitals. So this, let's say one is d z square dx square minus y square and d xy dy z and d zx. These 5 orbitals are there. So what we say that they will go to the excited states, that is when the spark field all are equally get repulsion. So all the 5 orbitals will equally go to the excited states 1 5. After that, what will happen, that when it is near field, it is when far field, and when it comes to the near field, then where that actually the ligands coming, so that will be get excited, and whichever due to far field they get excited, now they know that the ligand is not coming to them, so they will again come to the ground state. So here that if ligand is coming towards that axial positions, then only axials will be go to the excited state, and the non-axials will be, these are the non-axials will be come to the ground states, means again they will be come to the low energy state. Okay, so this way the d orbitals get redistributed. So when that this is happen when near field, this is happen for near field, means that how actually the ligands is coming, this is not actual ligands approaching. Here the actual ligand is approach, that we say that whenever you are in the track, it says these are the tracks, now you are in this track, it says you are in this track. So now if train is coming from here, train is coming to here, this is suppose coming to in your track, and this is one other persons, and this is another persons. So now that when train is coming to this track, let's say whenever train is here, now that all will feel that train may come to this track, train may come to this track. everybody will get afraid that train is coming to my trap. But when train is nearer to here, then only we understand that train is only coming to this track, train is not going to this track. So whenever this track, this means this far field, and these times everybody has afraid it of, everybody afraid that train may coming to their particular trap. But when train is nearer, then only they understand that no, train is coming, not coming to this particular person's track, only coming to this track. So only this will get more excited, means more afraid, other will be, that afraid will be gone. Okay, so when it is near field, likewise that whenever this is far field, all are getting excited state. Okay, and whenever it is nearer, then only and this is coming to this, so only this will get excited, other that whatever they get excited, they again release their energy. So this that energy of d orbitals get redistributed. Okay, so while these redistributions, whatever the energy, let's say this is that initially they have that zero energy, so let's say they have 0 joule. Okay, so whenever they get excited state, so they get some energy, they gain some energy, let's say they got that 1 joule energy. Okay, and now that this all the pipes totally 5 persons have that 1 joule energy. But now when the near fields, that ligand is coming only to this axial cases, or octahedral case only coming to the axial, then only these two will get, get excited state, and other energy should be released. So this 1 joule will be only for this case only getting that need high energy. For this case it need to release the energy, so this 1 joule will be again redistributed in between this. Okay, so you distribute it in such a way so that this and this get that equal energy. Okay, this 1 joule will be distributed equally in between this and this. So if you want to redistribute it equally, then what you see that here also will give that 1, so here you will also give half, for them also you have to give the half, so that half plus half equal to 1. Okay, so for that how they used to solve that, here that 2 is there, 2 into, so if I give that half, then you see that here 2 are there, 2 into half, that is going to be get that is 1. But here that 3 is there, 3 into half, that is going to be the 3.2, that is going to be 1 point something value, 1 point some value. So this value is getting high, this value is little high, this is 1 point that is 1.5 something. So this value is getting high, so I will not distribute it half and half, I distribute it such a way that both case I should get that one, means same I want to distribute it. I will not give this to half, I will give this such a value that, so that both the cases I will get that same. Okay, so for that what they did, let's say they will give to them, this is 2, so they will give them 2, so let's say 0.6, and for them they give that, let's say 0.4, so that now if you multiply here 2, then we are going to get 1.2. Now if you multiply it 3, then we are getting again 1.2. So likewise they distributed this equally, this whatever the energy, this is some x energy, let's say, that will be equally redistributed in between them. Okay, so this way that how that redistribution energy. So while this redistributions, the amount of energy released, okay, so the amount of energy released, that is called with the presence of ligand, so their ligand is coming, so with this presence of ligands, the amount of released energy is called that crystal field stabilization energy. Okay. Now whenever we are going to calculate that CFSE, that is crystal field stabilization energy, so we can calculate for two cases. One is for that is octahedral case, and the another for tetrahedral case. Okay, so we can calculate for square, planar, all these things, but now I will mainly focus on that octahedral and tetrahedral case. Okay, octahedral and tetrahedral case. So for this case, what happened that there will be have some chance of pairing. So we see that the relationship between octahedral and tetrahedral is octahedral. So this energy is delta naught, and if tetrahedral, then that is delta T. Let's say if it is tetrahedral, 1, 2, 3, 4, 5. So tetrahedral means ligand are approaching in the non-axial side, so non-axial will get excited 1, 2, 3, and axials will be down. So this very center, that is here delta T. For this octahedral, there is delta naught. Okay, so this is the distance between this. And what is found that octahedral delta naught, that is always greater than delta T. And the relationship between octahedral and tetrahedral is delta naught is equal to 4/9 delta T. That means we see that this is nearly delta naught is double. That says this 2 delta naughts is equal to 8/9 delta T. So this delta naught is nearly double of delta T. So this delta naught is always greater than delta T. Okay, so this delta T value is very less. So while we are doing that, we'll discuss. While we are calculating the CFSE, there is a chances of pairing, and what it found that the pairing energy is always greater than delta T. And if pairing energy is greater than delta T, on that case there will be no chance of pairing. So in tetrahedral case, we will see that no pairing will occur. No pairing will occur. It means that here what you see that always high spin complexes will form. Okay, for the case of tetrahedral. And for the case of octahedral case, here that pairing energy is that is greater than less than delta naught. So here the chance of pairing will happen. Here pairing occur. Here pairing occur. So here may low spin or high spin complexes. So both have chance. But for tetrahedral case, we will not look for pairing. So always we have that high spin complexes. Okay. So how it is? Let's take the examples. So you have that configuration like D1, D2, D3, D4, D5, D6, D7, D8, D9, let's say D0. This type of configurations may have in the metal ions. So for this case, for D0, D1, D2, D3, up to this, for octahedral case, let's say for octahedral case, then up to this there will be no chances of there is no chance to check that whether it's high spin or low spins. Okay, and for this d8, d9 and d10. And for this case of d8, d9, d10 also, there is no need to check that whether high spin or low spin. So here no need to check high spin or low spin. Here also no need to check high spin or low spin. Okay, but for this case we will check that high spin or low spins. Let's go check high spin or low spin for octahedral case. So let's say if you have that d4, and if that I have already told that 3D series and close to oxidation state, then up to En in spectrochemical series all are weak field ligands. Okay. After that all will become strong field ligands, and if it is 3D series and close to oxidation state, then up to water all are weak field ligands. Weak field ligands except cobalt 3 plus, and because this cobalt 3 plus, this is always have low spin complexes, means for except cobalt 3 plus, because all ligands act as strong field ligands for the case of cobalt 3 plus. Okay, except that is halogens X and N3 minus and H2 minus and HCl minus. This only leaving this, all ligands are strong field ligands for cobalt 3 plus. Okay, then all first oxidation state up to water are weak field ligands except this. So these are the 2 points for checking that high spin and low spin. And we know that for case of 40 5D series, it may be +1 or +2 or +3, all are that is strong field ligands. Okay, and if it is 3D series and oxidation states, these are the oxidation state. 3D series and oxidation states are +4, +5 oxidation state, then also all are strong field ligands. Okay. So this I have already discussed how to check that high spin and low spin complexes. So now I'm talking about of that rigid So for this case we will check that high spin or low spin complexes. So if it is D4 and if it is high spin complexes, then what you will do that case, this will be 1, 2, 3 and 4. And now if you want to calculate the CFSE, then how will you calculate the CFSE? That is, we know that this will have the 0.4 sorry 0.6, this have that minus 0.4. So you will add it of 0.6 and here minus 3 into 0.4, that is 0.6, that is going to be minus 1.2. So that value is going to be minus 0.6. This way you can calculate that, just multiply with this into this value and this with this value. Okay, That's how we calculate the CFSE. And if it is D for low spins, then how we'll do that? This case, all will be down 1, 2, 3, 4. Okay. So for this case, CFSE will be, but so there is no any things in the above, only down. So that is 4, and down case, what how much we multiply with? Minus 0.4, 4 into minus 0.4. That is going to be get 4 for the minus 1.6. Okay, and if it is D5, let's say for high spins, then on this case, how much you will get? That is 1, 2, 3, 4, and 5. So CFSE will be, you say that that will be 0. Why? Because you see that that is equally whatever that this, then this, and you know that this and this are equal, and this is positive case and this is negative case. Then this has to be equal, because what you say that they are equally redistributed. Okay, so if you calculate also, you can find that CFSE is equal to, here it is 0.6 we multiplied, here we will multiply by minus 0.4, that is 2 into 0.6 plus 3 into minus 0.4, that is going to be 1.2, that is minus 1.2. So the value will be the 0. Okay, so like D5, D10, where that all are filled, then that has to be the 0, because this is equally redistributed. Okay, so this case we can check that for D8, D9, and D10 there is no applicable of high spin and low spins. Why? Because you see that if it is in D8, okay, let's say I'm talking about of high spin, let's take high spin is possible, then let's here this 1, 2, 3, 4, 5, 6, 7, and 8, and let's say it's D8 low spins. Here also you see that 1, 2, 3, 4, 5, 6, 7, and 8. See that equal electron distributions is whatever it is same. Electron distributions are same. So here that either high spins or low spin, both the cases electron distribution same. So that's why we say that D8, or it may be D9, or it may be D10. Here that for both high spin and low spins, the electron configuration is same. So we say that D8, D9, D10 will not apply about of low spin, high spin, because both the cases will get that same types of electronic configurations. Okay, so now while calculating the CFSE, but actually general is, so we say that here that pairing will be possible. While we are doing pairing, we have to give some energy. So this is actually how calculated. Let's say we have this, let's say I'm saying this is A, let's say I'm going, this is B. Okay, so this is now this is, let's say this is B, and B electrons we have, here A electrons we have. So what you say that B into whatever that this value is, how much we have to multiply, 0.6 plus here how much I have to multiply, electrons are A, then this is minus 0.4 into A. Okay, after that this one into delta naught, because this is delta naught, After that we have to do that pairing. Let's say pairing electron is M, and let's say this is P. This is that number of electrons in the pairing. Okay, number of pairing electrons, and this is that, let's say they will give that pairing energy value, whatever they give the pairing energy value. Pairing energy, this is generally given, and this is also delta naught, this is also generally given. Okay, so if this is given, then we can calculate the CFSE by using this way. Let's say we have that case. Let's say I have this case. Let's say I have that D7. Okay, D7 high spin is there. For this case, let's say D7 low spins, so that I will do the pairing. So 1, 2, 3, 4, 5 and 6. So for this case, how will do that? And so this will be that CFSE. Then what is say that what this is the B, so B electron is 0, so this value is going to be 0. So here B is equal to 0, no electron is there. And A, we have that 6, so 6 into minus 0.4. okay, that is into delta naughts plus I will add that pairing energies. How many? M is equal to here 1, 2, 3, so 3 are pairing, so M is here, M equal to 3, so that is 3 into that pairing energy, whatever it will give. Okay, so this way we can calculate it. But you see that here, this is our we assume that this may be. So for this case, another also will check that D7 high spin case. So for this case, always check both the possibility. Why I'm saying, let's say D7 high spin, then 1, 2, 3, 4, 5, 6 and 7. So here what we see that both the cases, one will be pairing will definitely occur one case. Either you will do that low spins or you do the high spins, this pairing will occur. This and this pairing is occur, either you do the high spin or low spin. It means that it will be definitely this will be to the pair, there is no other way. Okay, so this pairing is definitely occur, so this and this pairing definitely occur, either you do low spins or do high spin. So one is only getting pair while you doing the pairing. So for this pairing energy, we only give that one pairing only. Okay, so in this way we will check the both the cases. Why I'm saying that, for this electronic configurations of D7 case, there is a two possibility, either you do the low spin or do the high spins. So if you do the low spin, then we have to do like this, and if you do the high spin, you have to do like this. So for both the cases, the two has to be the pair. It means that while you doing the low spins, only one we have to be in the pairing. So that's why your pairing energy is only 1p, not 3p. So this will be only 1p, not 3p. Okay, 3p is not. I will do not 3p, that is 1p. Similar case, if you look that, let's say if I'm talking about a D4, let's say D4 case. So this for high spin, if I say, then this is like this. Here 1, 2, 3, 4. Okay, and if I talk about a D4 low spin, then this will be. So where is high spin, where is low spin, that depend on the ligands that I have told. Okay, so if it is low spin, then this is 1, 2, 3, 4. In this case, CFSE will be, it is In this case, CFSE will be, that is B is 0 here, so that will not take. A, that is here, how many, 4 into that is the value is multiplied by minus 0.4, and that is delta naught, plus here pairing is 1, so here I will do that 1 pairing. Why? Because whenever I do that high spin, then there is no pairing occur. This I am giving by forcefully. Okay, so this case CFSE will be like this, 1 pairing will be there. For this case CFSE will be that is here 0.6, and this is 3 into minus 0.4 delta naught. This is the CFSE for this case. So if there is no chance of pairing with high spin, then that pairing will be taken as it is. Okay, let's say if we have that D5. So first is that high spin, then we see that, and D5 low spin. For this case, let's say D5 high spin, so 1, 2, 3, 4, and 5. And if it is low spin, then 1, 2, 3, 4, and this is 5. For this case, if I say that CFSE, for this case CFSE will be, for this case we see that CFSE will be 0, and for this case we see that CFSE is, that is here 1, 2, 3, 4, 5. So 5 into minus 0.4 delta naught plus how many pairing, 2, or 2p. Okay, so since that we'll check both the cases, high spin and low spin. For high spins, no pairing is there, so this we are doing that by forcefully, so we have to give that 2p. Okay, but if we see the D6 case, let's say high spin and D6 low spins, so D6 high spins like this case, so high spin, then 1, 3, 4, 3. Spins, then let's say this is 1, 2, 3, 4, 5, and 6. And low spin, then 1, 2, 3, 4, 5, and 6. So you see that for both the case, for this case CFSE is equal to how much, that is 5 will be 0, and this is minus 0.4 delta naught plus 1 pairing is there. Okay, so 1 pairing is there, so let's check that how much we are giving for pairing energy. So you check that here for both the case, for both the case, for both the case we see that here pairing is there, either you doing high spin, low spin, also 1 pairing is there. So in this case 1 pairing will be cancelled, because for both the case if you not do the pairing, if you do the high spin also 1 pair is possible, so this is come naturally, so this will not add. If you calculate that CFSE for this case, then it will be what, that is 6 into minus 0.4 delta naught plus, that is how much, 2p, not 3p. Why? Because this one is coming automatically, because if you do high spin, then also pairing is happen, so this will be the CFSE. Okay, so this way we can calculate that if it is any common both for high spin and low spin, then that pairing will get cancelled, and without adding that we will calculate that to the CFSE. Okay, so now the question is, let's say we have that D5 Yes, then what we say that this will be like this. So 1 2 3 4 5. So for this case CFSE is 0. Why? Because this is equal distributed and this is equal field. CFSE is 0. Let's say if we have that D6, let's say that is high spin, then 1 2 3 4 5 and 6. So this one I will calculate the CFSE very quickly. Let's say this is that summation of this one. This is the summation of D5 plus D1. That is, I can write here, that is 1 2 3 4 5 and this one. Okay, so this is always 0, only this. So downside, how much we are multiplied by? Minus 0.4. So CFSE is minus 0.4 delta naught. Okay, likewise we can calculate that CFSE in a quickly manner. If it is D7, then how will calculate it? 3. So let's say 1 2 3 4 5. Then let's say this is high spin, 6 and 7. So this is going to say D5 case, that is 0 plus 2 is there, then 2 into downside, so minus 0.4. That is going to get minus 0.8 delta naught. Okay, so for that high spin case, we can calculate like this: D7 D8. Okay, if you have that D8 high spins, D8 high spins case, this is 1 2 3 4 5 6 7 and 8. Okay, for this case, first down D5 will be 0 plus then 3 is there, so 3 will be 3 into minus 0.4. That is going to be minus 1.2 delta naught. Okay, so likewise D8 D9 D10 we can calculate that very quickly manner. Okay, so this is all about of that CFSE for octahedral case. And if it is tetrahedral or tetrahedral case, I says that this delta T is less than pairing energy. So if you want to do the pair, then we should have that more pairing energy. Suppose we want to go to some place, then we have that amount of money to go to that place. If we don't have, then we will not go. So likewise, if you are doing the pairing energy, if you are doing the pairing, then you should have more pairing energy. But delta T is less than pairing energy, so it can't do the pairing. Okay, so here every case that will be that high spin complexes. So here always high spin will occur, and pairing there is a non chance, so we no need to have pairing energy. So here that CFSE is always whatever, let's say B to that is 0.6 plus A. Let's say this is B electron, this is A electrons is there here, then minus 0.4, or this is delta T, and B is number of electrons in this case in axial orbitals, and A is number of electrons in non-axial orbitals. Okay, so likewise, so here there is not happen any pairing. Let's say if it has that D6, so we can't write here as low spin because the low spin never occur. Always it will be the high spin. So we can't do that like this. We can't do 1 2 3 4 5 6. This is not possible because it will always not do the pairing. So this is always become D6 high spin only. That is going to be like this. So 1 2 3 4 5 6, because here not pairing is not possible. So that is all about of that octahedrals and tetrahedral and how to calculate the CFSE. Another one point that is for whenever I am giving these values here, here I will write that EG and here is T2G. Why this for octahedral? What is there here that what we say that is cos is present. Cos means center of symmetry is present. So if center of symmetry is present, then EG and T2G. But for this case, oh sorry. So for tetrahedral, that is it will be not like this. It will be sorry. Axial will go above and this will be down. So this is the octahedral case. Okay, and it's since here for tetrahedral COS is absent, so we will not write T2G and EG because this is EG and T2G applied whenever cos is present, but here cos is absent, so you simply write T2 and E. Here also T2 and E. Okay, now that electrons we fill, then 1 2 3 4 5 6. Okay, because no pairing is happened, so this high spin low spin is not possible, so this is always high spin. Okay, so after discussing this amount of some points about of that CFSE, now I'm moving to that applications of CFSE. So with the help of CFSE, what applications are there? Okay, how you use that CFSE. So if you study anything, then you should know that what its applications. So using this CFSE, what things we can find out, what things we can calculate. Okay, so now we look at applications of CFSE. So if you able to calculate the CFSE, then we have we will understand that we can calculate lot of it has applications. So it has applications, let's say applications in if you want to calculate that Spinels, whenever you want to calculate the Spinels, on that case this CFSE will helps to calculate that Spinels, means that helps to identify whether it is normal Spinels. These Spinels are two types. One is normal Spinels, another is inverse Spinels. So while calculating the CFSE, we will differentiate between normal Spinels and inverse Spinels. Okay, so this is helped by the CFSE. So CFSE helps to identify that which is normal Spinels and which is inverse Spinels. Okay, so CFSE helps to distinguish normal spinel and inverse spinels. Similarly, we have that applications of that is lattice energy, and this let's say 1 2, and we have the applications of hydration energy, and we have that applications of that is stability of complexes. So for doing the stability of complexes also, CFSE has a very big tools. Okay, so there is a lot of applications, so we will discuss one by one. So first we will discuss on that application of CFSE in distinguish between normal spinels and inverse spinels. Okay, so first applications for today class is spinels. So now let's say that what we mean by the spinels and how that CFSE helps in distinguishing the spinels. So spinels are nothing but that is one type of lattice crystals in solid state chemistries, and that is always have the ligands, that is weak field ligands. Okay, for this Spinels, what you see that this is a crystal lattice, this is a crystal lattice in solids which have the general formula of AB2 X4. Okay, so this is that what that Spinels mean, that it is a one type of crystal lattice which have the general formula of this AB2 X4. So now what is AB, what is A, what is B, what is X? So A R, you see this is always A is always any diketons. Okay, and B like diketons, like any diketons, it may be transitions metals or it can be non-transitions metals, so any diketons. And B is always triketons, any triketons, it may be transition metal or it may be non-transition metal. Okay, and this is ketons. Okay, these are all the keton. And what is X? X is that anions. This is always anions. Okay, and this is we say that always weak field ligands. Weak field ligands, that's like that which I will be formed like O2 minus, this type of ligands, any F ligands, any this type of ligands. Okay, any ligands which are actually weak field ligands. So what we understand that here always high spin complexes will form. Okay, so from here what we understand, since this is always weak field ligands, this X is always weak field ligands. It means that what we understand, that if it is weak field, then always high spin complexes will form. Okay, so there is no low spin complex will form in this crystal lattice. Okay, so now that says that what is that, now formula is AB2 X4. Okay. So here what you say that one, that is A is always diketon, one A2 plus is there, and B is 2, B is there, and that is 3 plus is there. Okay, and that is X, and onions is there. Okay, that may be the charge, that it may be halogens, it may be any oxygens, any weak field ligands. Okay, so it can form this formula. Okay, so the generally this AB2 X4, this type of crystal lattice are most common crystal lattice are like we can say that MgAl2O4 minus, this type of crystal lattice O4, and generally you see that MgAl2O4 or like said MnAl2O4, this type of crystal lattice we have. So any crystal lattice, that must remember that this X will be that weak field ligands that cannot be strong field ligands, and this is any positive cations, any diketons is any diketons. Okay, so now that our work is not to say that what how many Spinels and which type of cations, which type, and here that main tasks for us for this calculation application of CFSE is that distinguish between normal spinels and inverse spinels. So what are the normal spinels and what are the inverse spinels? So before I'm going to discuss on that, what we say that in a crystal lattice, what we see that here we have that one positive cations is there, positive cations and negative cations and anions are present in a crystal lattice. Okay, so whenever this case, the anions always make the crystal lattice state for the crystal lattice. The onions always form the crystal lattice, and what the cations will do, these cations they used to go to the, while forming the crystal lattice, wherever you do any crystal lattice, okay, wherever how much crystal lattice you will do, there always had some voids. Void means some gap will be there. So this onions always goes to that gap of this crystal lattice. It is go to the gap or void, gap, or we use that in chemistry, that is voids. So these cations always go to the voids of the crystal lattice. Okay, so the onions form the crystal lattice, and this voids goes to the voids of the crystal lattice, that gaps in the crystal lattice. So whenever you pour that any crystal lattice, let's say this is one Spinels, if you form this, there will also having some voids is there, in between one gap is there, or you can form like this, then also these voids are there. So this, in this voids, this cations will go, and this anions form that this type of crystal lattice anions form, and this cations goes to this voids. Okay, so that's what we studied in solid states, that onions form the voids, onions form the crystal lattice. This is crystal lattice, any crystal lattice that is formed by onions. And what that metals will do, so metals or any cations, what they do, cations are generally that metals, so these cations will go to these voids, wherever this voids is there, wherever this void is there, these cations will go. So wherever the voids is there, these cations will go and go to that voids. So that what we studied in solid state chemistry. Okay, so now what I am going to study, that we studied in solid state chemistry, voids are two types of voids are possible. One is tetrahedral voids, these voids are two types voids are possible. One is tetrahedral voids, another is octahedral void. Okay, so these cations, so here how many cations we have that 3 cations. Voids we have that formula is, general formula of Spinels is Ab2X4. Okay, and this is plus 2 cations, this is plus 3 cations, so total 1 of dication is there, 2 of trications is there. Okay, so there is total 3 cations are present, total 3 cations are present. So out of these three cations, which will go to tetrahedral bonds, which will go to octahedral bonds, that on that basis we have that normal spinels and inverse spinels. Okay, and this crystals is always formed by these anions. So now that how you distinguish that whether it is inverse spinels and which the normal spinels, that is discussed by these cations, which cations goes to which bonds. Okay, so there is three cations are there. Okay, so out of these three, which cations go to tetrahedral bonds, which cations will go to that octahedral bonds. Now we know that generally this spinels we have one is cations, another we have the anions. Anions will form that crystal lattice, forms crystal lattice, and that crystal lattice is generally that base center crystal lattice. Base center crystal lattice it will form, that is FCC. Okay, so in FCC what you see that FCC whatever you see that one each, we say that this is that non-primitive types of unit cells crystal lattice, that is one will be at body centers and others are at corners. Sorry. One body centers and we have that base center. Okay. And at the corners, always it is present, and with that what is say one body centers and another is at base center. So body center is one and face center contributions is how many face centers are there total, that is see that octahedral bonds, this types of this. So how many are there? 1 2 3 4 5, these are the corners, and at the base centers these are the base centers. Let's say this is a base, this is one space, let's say these are the base. Okay, these are the space. So in this space at the center is 1. Okay, this center is 1 and this center is 1. So total how many faces are there? Top 4 tops are top 1, below 1 2, and the sides 2, that is 4, and back and front, that is 6. So 6 space and each contributions is 1 upon 2. Okay, so that total is that is 1 plus 3, the total is 4. So for FCC we will get that is 4. Okay. Similarly that cations, so lattice crystal lattice is 4. Okay, this is the lattice. Now that cations, this can be positive cations, sorry, dications, and this can be the trications, that is 2 cations. Okay, so now that which will go to that which cations, that we have to say that now that these cations. So the total bonds are two types of bonds are possible. I says bonds are two types, that is tetrahedral bonds, another is octahedral bond. Okay, now that tetrahedral bonds and octahedral bonds both are possible. So for tetrahedral bonds, what we say that this is in between the corners, one plus, that is at body centers, one at body centers, and this tetrahedral bonds. Okay, one is body centers and another is in between corners, that is the present. So body centers is always contribution is 1, and in between corners, that is so actually this one will discuss more in between corners, and that total is for tetrahedral bonds, that is 8 is there. Okay. That we will discuss while drawing the structure while you are studying that solid state chemistry. The total is 8 bonds are there. Okay, for tetrahedral bonds, and for octahedral bonds, what is that? Here one body centers, one is present at body center plus, and others are at edge centers. So totals will be, this is 1, contributions 1, and this is edge center, that is 12 edges are there, so 12, and that contributions is that is 1 upon 4. This is 1 plus this is 3. So this is also 4 octahedral bonds are there. From here we see that tetrahedral bonds are 8, octahedral bonds are 4, and the crystal lattice are 4. Okay, so now that whether A2 plus cations will go to tetrahedral bonds or trications will go to the octahedral bonds, that is depends on that what the CFSE, that CFSE will tell that whether dications will go to the octahedral bonds or trications will go to the tetrahedral bonds. From here what we understand that octahedral bonds is equal to this lattice points, that is equal to 4. Okay, but this tetrahedral bonds is just double of the lattice points, that is equal to 8. So now whenever I says that, let's say we have one dications we have and 3 trications is there. Okay, now let's say that this, let's if this is going to tetrahedral bonds, let's say it is going to tetrahedral bonds, then what will say that how many tetrahedral bonds are there? 8 tetrahedral bonds are there. Total tetrahedral bonds is equal to 8. So how many trications is there? So 1 dications presents, that is A2 plus. So if that one dications, 1 A2 plus goes to tetrahedral bonds, then what you say that how much it occupies. Okay, so 1A2 plus will occupies that 1 upon 8 tetrahedral bonds. Okay, because you see that one dicatons is there, and that is going to the, suppose that is going to the tetrahedral bonds. The total tetrahedral bonds are 8, so one dication is required 1 upon 8 of the tetrahedral bonds. Okay, so that is catons upon total tetrahedral bonds. Similarly, now let's say if this is going to, let's say that octahedral bonds, let's say that is going to the octahedral bonds. Now what you say that here, this is going to octahedral bonds, then total octahedral bonds are 4. Okay, total octahedral bonds is 4. Then how many dicatons are there? Dicatons, 2 dicatons are there. Okay, so this will how will occupy, that is 1 dicatons will occupy 1 upon 4, because that crystal lattice and this is same. Okay, so this is 4, so 2 dicatons will occupy 2 upon 4, that is going to be 1 upon 2. So this is that how it is occupies, that if let's say this is occupying to the tetrahedral bonds, this is also possible. Also this is also possible that let's say if one dicatons is there that occupies that octahedral bonds, this is also possible. Okay, if it is occupies the octahedral bonds, now we have that 2 dicatons. So since one has always occupied the octahedral bonds, now we have these 2. So for this case, this may occupy that tetrahedral bonds, and others will occupy that again that octahedral bonds. Why I'm saying that here, that if one is occupied with the octahedral bonds, because this is 1, and octahedral bonds is the high space, because octahedral bonds is greater than tetrahedral bonds. After occupying one octahedral bonds, again that space is there, so again another will go to the octahedral bonds, but one is remains, that will go to the tetrahedral bonds. Okay, so this will have 1 upon 4, and this is having 1 upon 8, and this will have again 1 upon 4. So now that this is tetrahedral octahedral bonds is occupied, so octahedral bonds that hybridizations will be D2sp3 or sp3 D2, and for this case the hybridizations for tetrahedral, that is always sp3. So this is depend upon that whether this is strong field ligands or high field ligands. Likewise we have the D2sp3 or sp3 D2, whether inner d orbitals filled or not. Okay, for this also that hybridizations will be that D2sp3. So now we say that the both cases are possible, either this case 2 this is possible, or this case 1 also possible. So which will the possible, that is explained by the CFSE. So either it will go or it will go, that is explained with the help of CFSE. While calculating the CFSE, we will say that which will go to this. Okay, So that's the why this Spinels applications of CFSE. Now that but how the CFSE helps to determine that which will go to where and whether it is normal spinels or whether it is inverse spinels. So we said that dicatons are, that is A2 plus 1 is there, and tricatons we have 2 tricatons are there. Now that which will go where, that's depend upon the CFSE. Okay, so what we say that the past case. Okay, so if it is goes like this, then this we will say that this is the normal spinels. And if it will go in the second case, then this will go to the inverse spinels. Okay, that if I do this quick, if I do this sum of, then what we say that for normal spinels, what I said that out of this and this, the tricatons will go to the octahedral bonds, that is B3 plus and other B3 plus, both will go to that octahedral bonds, and but this dicatons will go to the tetrahedral bonds. Then this is called the normal spinels. And what is said about of that, because for octahedral bonds, since its size is more, so that it will occupy the 2s. Okay, so anyway that octahedral bonds 2 will go, either 2 tricatons or 1 tricatons and 1 tricatons. Okay, because its size is more, so that we have to remember for octahedral bonds 2 catons must present, either 2 tricatons or 1. If 2 tricatons will present octahedral bonds, then that is called normal spinels, and this is go to tetrahedral bonds. Now other case, that inverse spinels, what we say that now what happened that, and this A2 plus go to the octahedral bonds. With this dicatons, only 1 dicaton is there, that is go to octahedral bonds, but it need 2, so another will go to the tricatons. If these go to that octahedral bonds, and remaining we have total is 3, so another remaining B3 plus, that will go to the tetrahedral bonds, because it occupies only 2. Okay, so 2 already went, so other will go to the tetrahedral bonds. So if it is there, that is called that inverse spinels. Okay, so this is for that normal spinels, this is for the inverse spinels. But how that, where in which case this will go, in which case this will go, that is explained by CFSE. So what that CFSE said, the CFSE also, CFSE simply says that if its CFSE is more, where for which catons the CFSE is more, that will go to the octahedral bonds. CFSE is very clear point. What the CFSE says, CFSE simply says that whichever the catons has that highest CFSE values, that will go to that octahedral bonds. Okay, so CFSE says that whatever the catons, if it has that high CFS value, that will occupy in the octahedral bonds. Okay, so competition is with octahedral bonds, which will go to the octahedral bonds. So CFSE clearly says that if you have that high CFSE value, then I will allow you to go to the octahedral bonds. Okay, so catons having high CFSE value prepare for octahedral bonds. So CFSE, that is cations having high CFSE value prepare for octahedral bonds. Okay. And what I say is that cations so first preferences which have that high CFSE value that will prepare to go to octahedral point. So we have to calculate the CFSE accordingly. We will say that which will go to CFSE, which will go to octahedral or which will go to tetrahedral. Okay, so I will conclude after this. Next class we will discuss from this point. Thank you.